So here we go. Um, so here, a planet is in orbit as shown below. So this is a planet right here. Where are two possible locations for the sun? Well, according to Kepler's first law, we know the planet has to travel in an elliptical path where sun is in one of the foci. So here's one and here's the other foci. So these two foci are where possible location of the sun could be. All right. Now, obviously, we don't know exact location, but it's just roughly around there. Okay. So that's number one. Number two, in the picture below, the area of section A is equal to area in section B. So we know that this area here has to be same amount of area as this area that planet sweeps out at same time, right? So part A, according to Kepler's second law, which section takes more time for the planet to travel? Well, they have to travel the exact same amount of time for planet to sweep out the area A and planet to sweep out area B, right? Um, so you could write down it takes same amount of time, right? For a planet to sweep out the area A and the area B. It has to be the same. Okay. What about part B? What does this mean about the speed of an orbiting body? So in order to sweep out the same area in the same amount of time, when the planet orbits around the sun, when it's closer to the sun, right? So when a planet or the orbiting body, right? Right, right, is closer to the sun, right? So basically area A, right? It will move faster, right? In order to sweep out the same area as B, right? In equal time to sweep out area B. So in order to compensate for the shorter radius, it has to sweep out much more angle to sweep out the same amount of area as B. So it has to travel faster, okay, when the planet is closer to the sun than further away from the sun. Okay? And write out the equation that represents Kepler's third law. Well, there are many ways to write this out, and they're all saying Kepler's third law. One will be the semi-major axis of a one planet cube divided by that planet's period squared is equal to any other planet's semi-major axis cubed divided by the period of that planet squared. Okay, so that is one form of Kepler's third law. Right? Another would be, it could be written as, right, flipped. Right? So the period of a planet A squared over the semi-major axis of a planet A cubed is equal to the period of planet B squared divided by semi-major axis of that planet B cubed. Now this is just flipped, right? But the ratio has to remain the same even if you flip it for the other planet, right? Another form of Kepler's third law, right, can be written as follows, right? Let me see if I could share that. You don't have to always have it that way, but it's nice to have it, okay? Um, where's the other formula? You could have it say that the semi-major axis of a planet cubed, right, is equal to g times the mass of the central mass, right, over 4 pi squared times the t squared. This would be another form of Kepler's third law. For this one, however, right, this must be in meters, and this must be in seconds. Right? There's no negotiation on that. And this g is a universal constant, which is 6.67 times 10 to the negative 11. It's just a value that you always have to use, okay? And we'll talk about the units on this later. This is the mass of the central body. Which means if a planet is orbiting around the sun, you put the mass of the sun in here. If you have a system where a moon is orbiting around a planet, then you put the mass of the planet in here. Not the moon, the planet, the central mass. So if you're talking about planet orbiting around the sun, central mass will be the sun, so you put the mass of the sun in here. Okay? Or if you have like a satellite, artificial satellite orbiting around a planet or different moon, or let's say, then you put whatever that satellite's orbiting around mass in here. And of course, it has to be in kilograms. Okay. All right. So that's it for Kepler's third law. So it could be this, it could be this, or any combination of algebraic manipulation of this, or it could be that. All right. All right. So last one. Let's take a look at number 4. The moon Io revolves around Jupiter, right? 0.048 Earth years. Io has a mean orbital radius of 4.2 times 10 to the 5th meters. Okay. If the Jupiter's moon Europa has a period of this many Earth years, then how far away is Europa from the center of Jupiter? Okay, so to give a visual representation of this, right? So here is here is Jupiter, right? And here's the big red spot on that Jupiter. And here is Io, right? And here is Europa. Okay? So they want to know, right? So this distance from the center to this. So this thing's going to travel in an elliptical path, but this ellipse is so uh, eccentricity of the ellipse is so small that it's almost circular. Okay, so this right here is the C for Io, and this Europa is going to be traveling around as well, and this right here is the C for Europa. Okay, so how can we calculate, right, how far away this is when we know that period of Io is equal to this many years, and period of Europa, right, is equal to 0.0097 Earth years, right? So to calculate that, right, we can use this equation, right? So we can say uh, C Europa cubed over the period of Europa squared must equal to, right, the C of Io cubed over period of Io squared. So if we solve for C Europa, that is equal to then cube root of, right, CIO cubed over the period of IO squared times the period of Europa squared. So if you plug everything in, here, cube root of CIO is this much, 4.2 times 10 to the fifth, right? You have to cube that. Divide that by 0.0048 squared times that by 0.0097 squared. So the year squared over year squared, the units will cancel out, right? And the meters cubed, cube rooted, will give you just meters. Okay? So hopefully we should be able to calculate this thing. And when you do calculate it, you're going to get something like cube root of this whole algebraic mess, right? Should come out to something like 3.0256 times 10 to the 17th right? And if you cube root that, you should get 67,330.4 meters, which is the same answer as that. Okay? How do you take cube roots? I hope you know how to do that, right? So if you have something like this and you take a cube root, you do, first you turn on the calculator, 3.0256. And if you raise that to, right, 1/3 power, and that's same thing as cube rooting, okay? So, I mean, obviously it should be times 10 to the 17th, but I'm just showing you how to take a cube root. So you take a cube root and that's what you should get. Or if you want to do like what this does, it's like 3.0256 EE17, right? Then if you want to cube root that, raise that to 1/3 power, and you should get that. All right. So just to give you an idea. Any questions? All right. So now you should be able to do the second page, right? And the third page for homework, okay, today. All right. And then we'll go over that on Monday. Okay, so you have the whole weekend to work on it. And yeah, that's it. Any questions? I would pay particular attention to 7, 8, and 9. Right? 7, 8, and 9. 7, 8, and 9 goes together, and 10 and 11 goes together. Okay, so like these two go together as one. Okay, and this goes together with all this. All right, so all right, so give it a shot, and hopefully we can go over that on Monday. Any questions? All right, then I'll stop the lecture for today, and we can finish the Galileo.